So this is Death Packet Saturday, and we're going to start off with the paired and one sample test quiz because we saw a couple of misconceptions, and we want to make sure we address those so that we end up with the best test grades possible on Tuesday. So scenario one, a recent study reported that high school students spend an average of 94 minutes per day texting. That's probably important. Jenna claims that the average for the students at her high school is greater than 94 minutes. She'll conduct a study to investigate this claim. Based on a random sample, well, that was nice of them, of 39 students, Jenna calculated a mean of 96.3 minutes and a sample standard deviation of 8.3 minutes. I want to talk to you real quickly about that 96.3. We know that it came from the sample mean. And I'm just going to tell you, it is just a really good habit to sit there and go, you know what? I'm going to label that as the sample mean right off the bat. And the reason being is we never ever want to include the sample mean as part of our null and alternative hypothesis. So our going in position was we need to start off by writing our null hypothesis. Well, the null is the status quo or the initial claim. And what was initially claimed was that it was 94 minutes. And then the alternative is her claim, and she's trying to show that it is greater than 94 minutes. Now, one thing to make sure that we know is the mean is always going to be an equal statement every single time. And then we know that our alternative is going to be exactly the same as our null, but we need to add an inequality. Well, obviously our choices were less than, greater than, or not equal to. They said greater than, so mu is greater than 94 minutes. All right, so that was step one. The next step is we need to go ahead and define a parameter. So in this case, let mu equal the true population mean amount of texting. All right, so let mu equal the true mean amount of texting, and it happens to be in minutes per day. But if as long as you had let mu equal the true mean amount of texting, we're good to go. Mean number of minutes texting, something along those lines is going to be really good to go for us. The next thing we need to address are our conditions. Well, the first thing is random sample. And as we noted when we read the question, they told us it was a random sample. It happened to be a random sample of 39, and that happened to be given. You don't have to give the number there. I just did just as a reminder to myself. So random sample, that happened to be given. The next thing I need to do is make sure my sample is less than 10% of the population. This is basically saying we're going to lose independence, but we want the amount of loss to be negligible. So we want a very, very small impact on, because we're not doing it with replacement. So 39 divided by 0.1 equals 390. Reasonable to assume that if it's a large high school, and we're just going to act like it's a large high school, reasonable to assume that there are at least 390 students who text. Why is that important? The sample is less than 10% of the population. Now, some of you are going to say, can I write the less than 10% of the population first? Absolutely. All right, but you do need to tell what it is you're doing. So whether you do the sample is less than 10% of the population at the top, or n is less than 10% of the population, that's fine. But at some point, you need to have some phrase that indicates you know why you have that condition. The number 3 condition is the normality condition. All right. And we can show normality multiple ways. They can tell us the underlying distribution is normal. They didn't. If they give us data, we can graph it to check to see if the distribution is normal. In this case, they gave us a sample size of 39. So 39 is greater than 30. The distribution of this is a key word here, sample means is normal by central limit theorem. Now, notice I said the distribution of the sample means is normal by central limit theorem. This is a really important distinction than saying the distribution is normal. We don't know what the distribution is shaped like. Matter of fact, I'm sure it's skewed because you know that there's some students who are going to text all the time. So the distribution, we're not going to say the distribution of the sample is normal. I mean, the distribution is normal. We're going to say the distribution of the sample means. But I only use that phrase if I'm working with central limit theorem. If I'm working with data, I'm saying the distribution appears to be normal. And we can't say that the distribution of sample means is normal because we're working with a small sample size, and central limit theorem only comes into play when our sample is 30 or larger. So unless we have a 30 or larger, we're not going to say the distribution of sample means, right? So we only say this when we're working with central limit theorem and our sample size is 30 or larger. Okay, so I'm going to scoot up here, make sure I have enough room to do all that I need to do. Those of you in my class have seen this ugly drawing, the boxes that I draw, and I apologize for all of you and Mrs. Lambs who get to read this beautiful writing as opposed to my pig scratch, but there you go. So writing my equation, t equals x bar minus mu s divided by the square root of n. And what is it that I'm actually looking at? And really this drawing just validates that I'm thinking about things correctly. Well, my mu, which is the center of the supposed distribution, is 94. But we ended, and this is the population mean. Then we have a sample standard deviation, x bar, of 96.3. And we want to know the likelihood that it's this extreme or more extreme. So we want the probability that x bar is greater than 96.3, which is the probability that t is greater than 96.3 minus the 94. The standard deviation we had was 8.3 divided by the sample size of 39. And by the way, they didn't ask for this, but I just want you to make sure that you're in the habit of it. My degrees of freedom in this case is going to be 39 minus 1 is 38. All right, so just make sure that you get in the habit of that. So I'm going to start plugging this into the calculator, and I'm going to go stat test t-test, and my mean was 94. 96.3 was my x bar. My standard deviation was 8.3. My sample size of 39. Make sure I have a greater than, so I should be matching my alternative. And I press calculate, and I find out the probability that t is greater than 1.7305 equals 0.0458. All right, and this is my p-value. So there's my probability. They gave us an alpha up here of 0.03. So I'm going to go ahead and make my comparison. Alpha equals 0.03. This is clearly larger than alpha. So my decision is going to be to fail to reject HO. One thing is, and I didn't do it just here, but you probably should, make these the same length. You're in the middle of a test and you don't want to get caught off guard, making a typo error. But 458 is clearly larger than 300. And I know you know how to do read decimals. It's just the stress of a test. If you make them the same length, you're less likely to make that error. So our P value is 0.0458. What did we do? We fail to reject the null. There is not, that keyword there is, make sure you don't forget not, there is not sufficient evidence at alpha equal 0.03 to suggest that the true population mean amount of texting. What was my alternative is, and my alternative was greater than, so I'm just going to write it in words, is greater than 94 minutes. All right. So our p-value is 0.0458. We failed to reject the null. There is not sufficient evidence at alpha equal 0.03 to suggest that the true population mean amount of texting is greater than 94 minutes. Well, what does this mean? We cannot support Jenna's claim that texting is more than 94 minutes. Or we cannot conclude that there's more than 94 minutes of texting. And that's a simplified term. And okay, I'm going to put pause on this. Actually, stop the recording. Oh. Ms. Lamb, when did you say that you saw that students were switching around in their conclusion?
Yeah, so some of the students in the conclusion were saying there was not convincing evidence to support that people are texting more than 96.3, which was the sample mean average. And that's not what we were testing. We were testing the claimed mu of 94. So you can't switch out mu for the sample mean.
That's really important, guys. We always are testing what's in the null and alternative hypothesis. We're not testing X bar. We never try to prove X bar.